Before we start, I want to remind you that I've already made a video on setting up STM32 programming environment, so this video will not deal with that again. I also recommend that you check out my ESP-IDF series, as they provide more detailed information about specific peripherals of microcontrollers in general, and only the coding part is specific to ESP32. First, we should know what bare metal programming is. It is a low-level type of programming that allows developers to interface with hardware directly without any operating system or abstraction layer. This means you will have to manage CPU registers, memory, peripherals, and interrupts manually. Essentially, it is the root of embedded development. This is helpful for a few reasons. Learners can gain an in-depth understanding of how microcontrollers work under the hood without any abstraction to simplify things, such as ST-HAL initialization code seen in the previous setup video. Relying on HAL doesn't offer you much insight into the MCU and ARM architecture. The product of bare metal programming has faster speed and is more resource efficient. This is because the layer of abstraction takes many resources of the system and thus slows things down. Still, it is not practical to employ this practice all the time, as debugging bare metal code is very challenging. You have to write almost all device drivers for the system, which is time-consuming for large applications. Certain features, such as concurrency, are tough to implement without an RTOS. You may also have heard of register-level programming, which is also a closely related concept. Registers are high-speed memory locations of a microcontroller's CPU. They hold data temporarily during the execution cycle of the program instructions, and they can hold many different types of data. Register-level programming means manipulating the processor's registers to interface with the hardware, and it is the main technique for bare metal programming. The two terms are often used interchangeably. Since we're working with registers, I'd also like to introduce the volatile keyword. When we define the register that we want to write to, we should use the volatile keyword. Volatile keyword removes unwanted compiler optimization to our variable. Say there is a register storing an analog to digital converter value, and the main task will run when this input value is changed. At first, the value is 0, as there is no input signal. We run a while loop to check it. The compiler would think that there is no point in checking this loop since it notices the value isn't changed anywhere in our code and does not run this loop. Setting it as volatile removes this assumption by the compiler and forces the system to recheck. Our usage of the volatile keyword in this video will be like this, where we create a pointer to a register's address provided by the documentation, then dereference it to write to our register. When doing bare metal programming, it's important to find the right documentation for your hardware. You need at least the datasheet and reference manual, which are simple to find with just a Google search. Please note that you must pick up the correct documentation for your specific hardware. This video also guides you on how to find relevant information from the documentation. Here I'm choosing the newer version of the documentation if available. If you are wondering about the difference between a datasheet and a reference manual, then a datasheet focuses on the physical aspect of the board, such as package layout or electrical characteristics, whereas the reference manual is more about programming and logic. Now we will open Visual Studio Code and create our project. Unlike the previous setup video, where the project is managed by STM32CubeMX, we will create an empty project. For now, all we care about is the main.c source file in the src folder. Like the previous video, we'll control the LED through pin B5, which means pin 5 of port B. Notice that pins are grouped into different ports. For example, port A has a pin 5 as well, denoted as PA5. Let's review the steps needed to blink this LED. First, we need to enable the GPIO peripheral of port B. Secondly, we configure pin B5 to work as an output pin by writing to its direction register or molder or mode registers. Finally, in our while loop, we toggle the pin B5 on and off repeatedly by writing to its output data register. There is a for loop that does nothing but acts as our delay. Now let's implement all these steps. STM32 structures its memory into many different blocks, but the part we focus on is the peripheral. Open the datasheet, and usually it's Chapter 5 for memory map. Here we can see that the peripheral block is the most detailed part, and its starting location is 0x4, followed by 7 digits of 0. Note that 0x means this is hexadecimal format. This is the base address of the peripheral block. Inspect things more deeply. We see that they are divided into smaller blocks like AHB1 and APB1. They are source clocks. We are interested in the AHB1 clock, and it has this address, which you can notice that it's the base address plus 20,000 hex. The 20,000 is our offset address. The concept of offset address is the address added to the base to arrive at a specific address, which is usually the register we need to find. Inside AHB1, we need the RCC address, and the offset is now 3800 hex compared to AHB1. Now I will explain why you have to pay attention to AHB1. Open the datasheet and search block diagram, which represents the relation between different parts of the system. We can see that all GPIO port is enabled by this AHB1 clock. This leads us to arguably one of the most foundational parts of STM32, RCC or reset clock control. RCC can control the clock of all other peripherals. Every peripheral needs a clock source to function. By default, most peripherals are disabled, as you don't want to waste power. To enable one, you must enable their clock source via RCC. We will open the reference manual and try to find the AHB1 enable register, then write to that register. Again, as the reference manual is more about programming, the info on register values will be here. You can either search by the table of contents, since we know it's in the RCC chapter, or search in this PDF for the word AHB1ENR, where R stands for register. The bit at position 1 indicates GPIO B status, and to enable it, we have to set it to 1. We can also see that the offset is 30, which means that with RCC as our base, we have to plus 30 to it to arrive at the register. This is the register we will write to, so we'll make this volatile. Now let's implement these addresses in our code. Note that UL means unsigned long, which should have a size of 4 bytes or 32 bits. Then we turn on bit 1 of AHB1ENR to enable GPIO-B. To do so, we will use the OR operation with this number, where only bit 1 is 1. Don't use the assignment operator, as you may accidentally change all the other bits that are meant to be used or reserved by the system. You may also check out this thread on how to manipulate one specific bit. Now the next step is to set pin PB5 as an output pin. In the reference manual, the GPIO section is in Chapter 8. Each port has these registers layout in the table of contents. Note that the offset is relative to the port, and in our case, port B. For now, I want to introduce you to 3 main types: molder or direction register, which is whether you want the pin to act as an output or input; ODR or output data register, when you want to set the output of the pin as 1 or 0, and finally, IDR. You can't write to the IDR or input data register. The input a pin received is stored in this register. To make pin 5 act as output, bit 11 and 10 of the mode register, which corresponds to pin 5, should be 0 and 1 respectively. If you are curious as to what alternate function is, it is when the pin is used for other peripherals, such as TX or RX of UART. Coming back to the code, we implement the address and offset of GPIO-B registers and write to the mode register. Finally, we will make PB5 output high and low repeatedly. This is done by writing the value of the output data register, or ODR, of the GPIO. Bit 5 of ODR controls the output of B5. We will perform XOR operation on it to change its value to the opposite state. This is followed by a for loop that does nothing but count to 1,000,000, which acts as a primitive form of delay. Build the project, then press F5 to start debugging, and you will see the LED blinking. Now, our small example worked fine, but we can optimize it further. You see, defining all these addresses with their offset is extremely tedious, especially when we build larger applications. STM32 Cube already has these headers fine with all of the addresses defined for us in struct, so we won't go through this step again. You may wonder, what is the point of using struct? It is actually taking advantage of struct alignment, as struct member has their member addresses arranged sequentially. Let's look at one such piece of code defined in the header file. As each member has a size of 4 bytes and they stack up, each member has an offset address of 4 bytes compared to the previous member. This matches the offset address mentioned in the reference manual. You can download the header files needed in the STM32 Cube F4 provided by ST through a Google search. Don't download through GitHub or the patch version. Navigate the file system as follows to find the core header file and STM32 F4 header file. You keep the core header files, then copy the F4X and system F4X along with the correct header file for your chip to the same folder. I have created a new blank project, then I copied all of this into the INC folder of my project. The INC folder actually stands for include, and this is where our project expects any custom header file will be. In the F4XX header file, it tells you that you need to define a symbol for your chip so that it can include the header file corresponding to your chip. You can add this as a symbol through CMake. Go to cmakelist.txt and add this line and replace the symbol corresponding to your chip. Try including the F4XX header file in your main.c and then build, make sure things work correctly. Once done, the code can be made much simpler. Recall that AHB1 enable is in RCC, so call the RCC struct with the arrow operator to access its member, which we need AHB1ENR. Modify the molder and ODR of GPIO just like earlier, and you are done. Compile and run will produce the same output as before. And that's it for this video. Thanks for watching, and as always, you can support my channel by dropping likes and subscribes, or even consider giving a small donation with my info under the description. Hope to see you again in my future video.